Have you ever looked up at the night sky
I think most people have, yeah.
and really looked and just felt, well, incredibly small?
Oh, absolutely. That feeling of just insignificance almost, faced with the sheer scale of it all.
Exactly. Like you're this tiny speck on a little planet just kind of whizzing through this vast, vast cosmos.
It's a universal feeling, I think. Pun maybe slightly intended there. Humans have always looked up and wondered, how big is all this?
And that's exactly what we're diving into today here on Cosmic Origins Revealed.
We're tackling the big one.
The really big one. Just how big is the universe? It's a question that's, well, it's fascinated people for basically forever.
It really has. And what's amazing is how much our picture has changed, especially, in the last 100 years or so.
Right. We're sort of in this golden age of finding things out, aren't we? Telescopes getting better and better.
Definitely. Constantly pushing what we can actually see, what we can measure.
It's kind of mind-boggling to think that just a century ago, our whole idea of the universe was pretty much just our own galaxy, the Milky Way.
That was the universe, as far as most astronomers were concerned.
Okay, let's unpack that. What was the thinking back then, say, early 20th century?
Well, the prevailing view was that the Milky Way contained everything. All the stars you can see, our sun, Earth. It was all thought to be part of this one single huge star system.
So the major question buzzing around must have been, are there other Milky Ways out there? These fuzzy patches people saw, were they inside or outside?
Exactly. Were those nebulae, as they call them, just gas clouds within our galaxy? Or were they, well, separate island universes? That was the crucial debate.
And what broke that deadlock? Technology, I assume.
Technology, yes.
Yeah.
Specifically, bigger and better telescopes. The construction of a new observatory on Mount Wilson in California was a real turning point.
Mount Wilson. Yeah, that name keeps popping up in the history of cosmology. What was so special about it?
Well, the vision behind it, particularly from George Hale, was to build the biggest, most powerful telescopes ever conceived to really tackle these fundamental cosmic questions. The giant 100-inch Hooker telescope, completed there in 1917, that was the instrument that changed the game. Its light-gathering power was unprecedented.
And enter Edwin Hubble, probably the most famous name linked with this whole story.
Absolutely. Hubble used that Mount Wilson telescope to meticulously observe these nebulae. He focused particularly on the Andromeda Nebula.
Big fuzzy patch in the constellation Andromeda.
That's the one. And what he found inside it was, well, revolutionary. He identified specific types of stars, Cepheid variables.
Okay, hang on. Cepheid variables. Why were they important?
Because Cepheids are what astronomers call standard candles. They have this really useful property. The rate at which they pulse, their period, is directly linked to their actual intrinsic brightness, how bright they really are.
Right, like knowing the wattage of a light bulb.
Exactly like that. So if you measure how fast a Cepheid is pulsing, you know its true wattage. Then you measure how bright it appears to us here on Earth.
And if it looks dim, even though you know it's a high wattage bulb,
it must be really, really far away. You can calculate the distance.
So Hubble found these Cepheid stars in Andromeda.
Yes. And when he calculated their distance, based on their apparent faintness, he found Andromeda wasn't just a cloud nearby. It was millions of light years away.
Millions. Wow, so definitely not inside the Milky Way.
Not even close. It was an entirely separate galaxy, comparable in size to our own. In an instant, our universe went from one galaxy to, well, at least two, and likely many, many more.
That changes everything. Our whole place in the cosmos.
It was a profound shift in perspective. The Milky Way wasn't the universe. It was just one galaxy among potentially countless others.
Okay, so the universe got unimaginably bigger. But the story didn't stop there, did it? Because these other galaxies weren't just sitting still.
No, that was the next huge discovery. Hubble and others kept measuring these galaxies, and they found something else. Almost all of them seemed to be moving away from us.
Moving away? How could they tell?
It comes down to the light they emit. You know the Doppler effect with sound, right? How a siren sounds higher pitched coming towards you and lower going away.
Uh-huh. The sound waves get compressed or stretched.
Well, light waves do something similar. If an object is moving away from you, the light waves it emits get stretched out. This stretching shifts the light toward the red end of the electromagnetic spectrum. We call it redshift.
Okay, so they looked at the light from these distant galaxies.
And they saw it was redshifted. And crucially, Hubble found a relationship. The farther away a galaxy was.
Let me guess. The faster it was moving away, the more redshifted its light was.
Precisely. The farther the galaxy, the greater the redshift, the faster the recession. This became known as Hubble's law.
Which points directly to the idea of an expanding universe. Everything is moving away from everything else, kind of like dots on an inflating balloon.
That's a great analogy. And if the universe is expanding now, it implies that in the past, everything must have been closer together.
All the way back to a single point.
If you run the clock backwards, yes, you reach a state of incredible density and temperature. That's the core idea behind the Big Bang Theory.
Which must have been a pretty radical concept at the time.
Oh, hugely radical. It took decades for it to become the standard model. There was a lot of resistance initially. It fundamentally changed our view of cosmic history.
Understandably so. So we've got an expanding universe born from a Big Bang filled with countless galaxies. But how did we learn more about those very early moments? Visible light only tells part of the story, right?
Exactly. To really probe the conditions of the early universe, astronomers realized they needed to look beyond the visible spectrum. Light is just one form of electromagnetic radiation. There's also gamma rays, X-rays, ultraviolet, infrared, microwaves, radio waves. Each tells us different things.
And opening up those other windows led to some big surprises, like finding the echo of the Big Bang itself.
You're talking about the cosmic microwave background, the CMB. And yes, that was a huge discovery, and actually kind of accidental.
Accidental? How so?
In 1964, two radio astronomers, Penzias and Wilson, were working with a very sensitive microwave antenna. And they kept picking up this faint, persistent background hiss. Noise.
Coming from everywhere.
Everywhere they pointed the antenna. It was uniform, day and night, all directions. They initially thought it might be interference, or even pigeon droppings inside the antenna horn.
Seriously, pigeons?
Apparently so. They cleaned everything out, checked all the systems, but the signal remained.
So what was it?
It turned out they had detected the residual heat, the afterglow, from the Big Bang itself. Light released about 380,000 years after the universe began, now cooled and stretched by expansion into microwaves.
Wow. The actual leftover heat from creation.
Pretty much. It's incredibly faint, corresponding to a temperature just under 3 degrees above absolute zero, about 3 Kelvin, a monumental confirmation of the Big Bang Theory.
And later space missions mapped this CMB in much more detail, didn't they?
Yes. Missions like COBE, then WMAP, and most recently Planck. They measured the CMB with incredible precision. They found tiny, tiny variations in its temperature across the sky, like parts per 100,000.
And those tiny ripples were important.
Incredibly important. They are the seeds of all structure in the universe. The slightly denser spots eventually grew via gravity into the galaxies and galaxy clusters we see today. WMAP data also helped pin down the age of the universe to about 13.7 billion years.
Okay, so we have a good estimate for the age. Let's get back to the size. You mentioned the observable universe earlier. What exactly does that mean?
Right. The observable universe is basically our cosmic bubble. It's the region of space from which light has had time to reach us since the Big Bang started, 13.7 billion years ago.
So you might think it's 13.7 billion light years in radius, right? Light traveling for that long.
That seems intuitive, yeah. But it's actually much larger. The current estimate for the radius of the observable universe is about 46.6 billion light years.
Whoa, hang on. 46.6 billion. How can it be bigger than the distance light could travel in the age of the universe? That seems weird.
It is weird, but it's because space itself has been expanding the whole time that light was traveling towards us.
Ah, okay. Like the raisins in the rising bread dough analogy you used earlier.
Exactly. Imagine a galaxy emitted light towards us very early on, maybe just a billion years after the Big Bang. That light started traveling. But while it was traveling, the space between that galaxy and us continued to stretch and expand.
So even though the light traveled for, say, nearly 13 billion years, the galaxy that emitted it is now much, much farther away than 13 billion light years because space itself expanded.
You got it. The expansion stretched the distance. So the edge of what we can see, our observable horizon, is about 46.6 billion light years away in every direction. That makes the observable universe about 93 billion light years across.
93 billion light years. It's just numbers that big are hard to even imagine, and that's just the part we can see.
That's just the part where light has had time to reach us. The entire universe could be much, much larger. It might even be infinite.
Infinite? Really? How could we even know?
Well, that's the trillion-dollar question, isn't it? Our current observations, looking at the overall geometry of space using the CMB, suggest the universe is very close to being flat on large scales.
Flat? Meaning like a sheet of paper, not curved like a sphere.
In a geometrical sense, yes. And a flat universe, according to Einstein's theories, is consistent with being infinite in extent. though it doesn't prove it's infinite.
What about regions beyond what we can see? Are they just more universe?
We assume so. The cosmological principle suggests the universe is broadly the same everywhere on large scales. But there are regions so far away that due to the accelerating expansion of space, they're receding from us faster than the speed of light.
Faster than light? I thought nothing could do that.
Objects can't travel through space faster than light, but space itself can expand at any rate. So light from those super distant regions will simply never reach us. They're beyond our causal horizon forever.
Wow. So there's definitely a universe out there we can never, ever see or interact with.
Seems very likely, yes. Whether the total amount of universe goes on forever,
Yeah.
we just don't know for sure.
It reminds me of Olbers' paradox, that old question. If the universe is infinite and full of stars, why is the night sky dark?
Ah, right. A classic thought experiment. If you had an infinite, static, eternal universe, uniformly filled with stars, then yeah, every line of sight should end on a star. And the whole sky should be blindingly bright.
But it's obviously not. So what's the catch?
The resolution comes from the things we've been discussing. The universe isn't infinitely old. It began with the Big Bang about 13.7 billion years ago. So light from stars beyond 13.7 billion light years hasn't had time to reach us yet. And crucially, the universe isn't static, it's expanding. That expansion redshifts the light from distant galaxies, stretching it to longer, lower energy wavelengths, making them dimmer and eventually invisible to our eyes.
So the darkness of the night sky is actually evidence for the Big Bang and an expanding universe with a finite age. That's pretty cool. Another cosmic insight from us here at Cosmic Origins Revealed.
It really is. The absence of light tells a story too.
What about the other possibility? A universe that's finite, but maybe wraps around?
That's another fascinating idea. Einstein himself initially favored a model of a finite but unbounded universe. The analogy is the surface of a sphere.
Right. You can walk forever on Earth's surface in one direction and you never hit an edge. You just end up back where you started.
Exactly. The surface is finite in area, but has no boundary. So maybe our three-dimensional space is curved back on itself in some unseen higher dimension.
Could it be shaped like something else? I remember reading about like a donut shape.
Yes, that's the idea of a non-trivial topology. The universe could be geometrically flat, but still finite if its topology connects back on itself, like a multidimensional torus or donut shape.
So if you traveled far enough in one direction,
You might emerge back where you started, potentially from a different direction. You could, in theory, see the back of your own head if you looked far enough with a powerful enough telescope, or see the same distant galaxies repeated in different parts of the sky.
that is completely wild. Have we seen any evidence for that, like repeating patterns in the CMB?
People have looked very carefully for those kinds of large-scale repeating patterns in the CMB data from Planck and WMAP. So far, they haven't found any definitive evidence. The results suggest that if the universe is finite and wraps around like that, the wrap-around scale must be larger than the current observable universe, so it could still be finite, just very, very big.
But the idea of an infinite universe, that still feels philosophically tricky.
It absolutely does. If the universe is truly infinite and contains a finite number of ways matter can be arranged within a given volume, then any specific arrangement, including, an exact copy of you, me, this room, our entire observable universe must repeat infinitely many times out.
Infinite copies of us.
That's the bizarre logical consequence of a truly infinite universe with random variations. It's a concept that stretches the mind, to say the least.
Understatement of the millennium. Okay, let's try to bring the scale down to something slightly more graspable. Those analogies are sometimes helpful.
They are, though they always break down eventually. One I like. Imagine the Earth is shrunk down to the size of a single grain of sand.
Okay, Earth equals grain of sand. Got it.
On that scale, our entire solar system, out to Neptune, would be roughly the size of a large building, maybe like Durham Cathedral.
Wow. From a grain of sand to a cathedral just to contain the solar system, that puts the emptiness out there in perspective.
It really does. Now, take it another step. Shrink that entire solar system, the whole cathedral, down to the size of that original grain of sand.
Okay, solar system is now a grain of sand.
On that scale, our Milky Way galaxy, with its hundreds of billions of stars, would be about 1,000 times bigger than the original cathedral, maybe the size of a small country.
That's staggering. And remember, folks, you're getting these mind-bending scales right here on Cosmic Origins Revealed.
And one more step. Shrink the entire Milky Way galaxy down to a grain of sand.
Galaxy, grain of sand. Okay.
Then the entire observable universe with its billions of other galaxies would be back to the size of that cathedral again. It's just layers upon layers of vastness.
It's almost impossible to truly comprehend. What about travel time? Those sometimes make it feel more real.
Right. Think about driving your car nonstop at highway speeds.
Yeah.
To get to the moon would take you over 5 months.
5 months just to the moon.
To get to the sun. By car, impossible. But let's say by a fast jet plane. Around 19 or 20 years of continuous flying.
20 years?
To get to Neptune, the edge of the planetary system. Thousands of years by car, hundreds by jet. And that's still just our backyard.
And the nearest star system, Alpha Centauri.
About 4.4 light years away. Our fastest current spacecraft, like the Parker Solar Probe, would still take tens of thousands of years to get there. Maybe 70,000 years or more.
70,000 years. It just underscores the sheer emptiness between stars, between galaxies.
Immense voids. And speaking of things we can't easily see, we haven't even talked about what most of the universe is actually made of.
Ah, yes, the dark side. Dark matter and dark energy.
Exactly. All the stars, planets, gas, dust, everything we can see, everything made of atoms like us, that only adds up to about 5% of the total mass and energy content of the universe.
Only 5%. So what's the other 95%?
Well, about 27% seems to be this invisible stuff called dark matter. We can't see it, it doesn't interact with light, but we know it's there because we see its gravitational effects holding galaxies and galaxy clusters together. It's like invisible scaffolding.
Okay, so that's 5 plus 27. About 32%. What's the rest? The huge chunk?
The remaining 68% or so is even more mysterious. It's called dark energy. It seems to be some kind of energy inherent in space itself that's causing the expansion of the universe to accelerate.
Accelerate. So the expansion is speeding up.
Seems so. This discovery, made in the late 1990s by observing distant supernovae, was another huge shock and earned a Nobel Prize. We have ideas, but we really don't know what dark energy fundamentally is. It's one of the biggest mysteries we explore here at Cosmic Origins Revealed.
So after all this incredible progress, 95% of the universe is still made of stuff we don't understand. That's humbling.
Deeply humbling. It shows how much more there is to learn. And that's why we keep building bigger, better instruments.
New telescopes on the ground, new missions in space, always pushing the frontiers.
Exactly. Telescopes like the James Webb Space Telescope are peering deeper into space and further back in time than ever before. Future telescopes aim to map the universe in even greater detail, probe the nature of dark energy, maybe even glimpse the very first stars. The quest continues.
Well, this has been an absolutely mind-expanding journey today, exploring the sheer scale of everything, right here on Cosmic Origins Revealed. It really does make you pause and think about our own little place in it all.
It certainly does. We've learned so much, mapped out these incredible distances and time spans, but that ultimate question, the true total size of the universe, still hangs there. Is it finite or infinite?
And it leaves you with that lingering thought, doesn't it? What does it mean if the universe is infinite? Or what if it's finite, but just unimaginably, staggeringly huge? What does either possibility tell us about reality, about existence itself?
Profound questions with no easy answers. That's what keeps cosmology so fascinating.
Absolutely. Something to ponder next time you look up at that night sky.
Indeed.
If you enjoyed this cosmic deep dive, make sure you subscribe to Cosmic Origins Revealed on YouTube for more exploration into the biggest mysteries of the universe. We'll see you next time.